Okay, so today we'll study some more aspects of file system. All right. So these are topics we'll cover. There are not many topics today, but more concepts we'll have to go through. Okay, so where we stand in terms of file system. Okay, we have covered. So this is the file system hierarchy. We have at the top streams. Just a minute. My pen is not. Just hold on for a minute. Okay, so this is what we have covered earlier, right? We have covered files, directories, indexes, etc. So we started from bottom actually. Architecture of file system in general. Okay, and now today we will study streams, which is basically streams are used by users. Okay, and below that we have file descriptors. If a user wants to use file descriptors directly, uh, they can do it, and in fact you have used it. However, to give more convenience to user and make the programming more efficient in terms of overall time or time for execution, then high level primitives are provided by standard library. Okay, so we'll look at what these streams are, how they are different from file descriptors, and so on. Okay, all right. And then at the end, maybe later lectures will come to IO driver and IO part. So we have completed almost half, 3/4 of file system uh, discussion, and maybe 2 classes will spend more. Then we'll move to IO, and then again we may come back to file system to connect both IO and file system. Okay, so this is the structure. Okay, so first bullet says the sequential access. So file can be accessed in multiple ways, right? First, we have seen there is a file position. When file is opened, it's nothing but a stream of bytes or a array of bytes or file. Okay, and then we have, when it's opened, that okay, file position is at the beginning, and as we go on doing operations, it keeps moving. Like we read, then read a byte, then file position moves to second byte, and so on and so forth, right? So this file position we can move by instructions itself. We can go, rather than going one by one, we can directly go to a certain place in the array, right? Okay, and that's called random access, the second one. Okay, so we can start from anywhere, and then this is actually used more in disk. Okay, now finally, whatever abstraction we have in terms of array of bytes translates into what happens underneath in a file system that's there on implemented on disk. Okay, so file abstraction, lower level file abstraction, which uses file descriptors, we have already covered. Okay, high level file stream we are going to study today. Okay, so let's see the need for high level file stream. Okay, so in order to understand that, we'll have to see what is the need for it. See, you have done programming using syscalls for file operations, right? Like open, close, read, write, etc. Okay, so can you think of what is the need for creating anything on top of that at the library level? Just think about it. Why? Why do you need? See, we don't see the need because we have not measured the performance. That's one thing. And second thing is that we have used very simple system calls. Okay. And if you observe the number of two things, first is that, sorry, the first thing is performance. Since we have not measured it, we don't know. And of course, number of parameters that you have to, arguments or parameters that you have to use in syscall is just too high. Okay, for if you do use many times these system calls, then there is a, you don't like to do that kind of programming because number of arguments can go up to 7, 8 or even more. Okay, and these are given at that level, OS level, because OS gives this interface to user for the flexibility. Okay, because a lot of things you can define, but in practice you may not use that, right? Okay, so we have this library given to us. Okay, and most of the time we use libraries. Okay, although you can directly use syscalls, which is second bullet point. Okay, third bullet point, you can see that syscalls has number of arguments, which makes programming complicated, that we have seen. Okay, discuss already that in more number of arguments are there, there's a good, every time you have to go and look at the manual and so on and so forth, right? So it makes life little difficult for programmers. Okay, while at the library function, the little simplification is provided in terms of these arguments. Okay, and also the service provided is called buffered IO service. Okay, we'll see what need for buffering in the next slide. And while syscall that you have been using does not provide buffered IO service. So if you use library functions, then it provides buffered IO service. If you use syscalls directly, it does not provide any buffered IO service. So now question that comes to your mind, what is buffered IO service? That will address later. Okay, so standard library, standard syscalls uses file descriptors, right? When you open a file descriptor is available to you. And then all subsequent operations, you'll have to just give the file descriptor name for reading, writing, and closing and so on, right? Okay, while in system library we have concept of streams. So streams ultimately translate into file descriptor. Okay, so stream is higher level abstraction available to us. So two examples are, if we use standard IO library, the third bullet, if you read, then open file, an open file is called stream. Okay, and then syntax is something that's given here. The stream is equal to f open. Now you note that we are using f here, f open, then the file name or path that we want to open, because we have to do, at the time of opening we'll have to give file name. Okay, and subsequently we don't, then we can use stream, subsequent operations, and then we have to define mode, reading mode, writing mode, etc., right? While when you use file descriptor, you would have seen that we'll get file descriptor here. You can see the last line, and then use open, and then give path name like the /home /kit /medax MADAGA medaxer, and then mode RD. Okay, all right. So there's a difference. So here, when you use open a file name could be the same, whatever file exists, and path is the same, that's given by directory in both cases. So first case, when you use library, you get a stream. Second case, you get a file descriptor. So there is subtle difference. Okay, so now we come to the concept why we need buffered IO. Okay, so note that note that when we looked at disk. Okay, and if you remember, if you remember it, then you will find the disk is partitioned. This is basically consists of number of circles, okay, or tracks, and then there is a sector. And so we say that, and then we have concept of blocks. Okay, so minimum transfer unit from disk to higher layers, which is OS, which sits on that, is a block. Okay, so block is an abstraction representing the smallest unit of storage on a file system. Okay, a block consists of number of bytes, but it is extremely hard. So the whole hard disk is designed in such a way, disks are designed in such a way that minimum unit that can be transferred is a block. Okay, okay, so inside the kernel, all the operations are done in a block. Okay, so it means that if you are reading a byte from a file, even then whole block is brought into the kernel. Okay, and then in turn kernel will send you the byte, to the user program. Okay, so if you want to, similarly for writing operation, right? Okay, so whole block is to be written back into disk even if you are changing one byte. All right, so but application, if you look at user applications, you open a file and get few bytes of data and so on and so forth, right? So you don't write a program thinking in terms of blocks. You write a program in terms of some abstraction, like you may manipulate bytes, or you can have strings and so on, right? Or array of certain sizes, or something, or some structure which is considered certain. So your abstraction is different, while file system or the hard disk thinks only in terms of blocks, and same is true for OS. Okay, so you may want one byte, but OS will get one block and do manipulation on that. So it's like you do one reading of one byte each time, 1024 times. Okay, one by one. So it will do 1024 block transfers if you use simple system calls. Okay, so it's very expensive. So instead of that, if we get full block at user space and put it in a buffer, then we can do this operation very easily, because you don't have to make so many system calls. It's just simple memory read, because part of address space. Okay, all right, so this is a concept. So instead of doing so many system calls, and we know system calls are expensive, and in turn OS is bringing the block each time you are making this request, it's very expensive process. Okay, to avoid that, you just get certain number of blocks into a buffer and do the manipulation as much as you want. Reading and writing, you can do both. And when after a certain point in time, when for example, or certain conditions, for example, when you're doing writing and that buffer is full, you write it down into hard disk. You transfer it to OS kernel, and kernel will write. Okay, any question with this concept? No? All right, let's move ahead then. So to improve performance, data can be buffered internally by delaying writes and reading ahead. Okay, so once you have data available in buffer, which is in user space, essentially it means in a RAM. Okay, then you can do a many operation onto it. Okay, and then it can be returned back to the disk. Okay, so in general, blocks are of 512 bytes or 1024 bytes or 2048 bytes or 4096 bytes or same. So half K, 1K, 2K, 4K or 8K. And buffers are just multiple of these. Okay, so it depends on OS. It depends on the design. Okay, now this IO library provides this a standard in a standard way, and they would have possibly done some simulation to find out what is the best possible buffer size. Okay, however, if you want to write your own buffering scheme, you can do so, because it's in user space. Nobody stops you from writing your own library or these functions. So in general, there are many mission critical applications where performance is really important, and they don't want to use library because library does it in its own way, is more generic in the sense that it takes care of every application and so on. So if you want to write a mission critical application or real time application, then you can optimize this buffer size in your own way. Okay, block sizes of course is usually not the choice of a programmer, because it's provided by kernel, until unless you can change block sizes, and you have power to change the block sizes in kernel. So assuming that block sizes are fixed for you, buffer size you can design of your own. Okay, all right, any question? We need buffer.
So mainly to improve the performance, so
How?
that we could delay writes and reading ahead.
Okay, very
Like,
good. And because we use less system calls, that's it.
yes.
Okay, all right. We use similar concept sometimes in the last course where we delayed writing back. Can you think of that scenario?
Caching.
Yes,
Yes.
caching, where we keep caching in one of the schemes, we delayed, right? Was it write through or write back?
Right. I don't remember it exactly. I think it's
Yeah,
right.
write through says that whenever you write, it goes to every level of memory, right? Okay.
Yeah.
Write back is where you delay, if I remember correctly. Okay, all right. I request you to visualize. When you read something, try to visualize it, right? Once picture you form, then it is easy to remember. Okay, so let's move on. So this buffering is done in user space. It's done transparently. I mean, user doesn't know about it, right? So when data is written, is stored in buffer inside program header space, and when data reaches certain size, say buffer size, entire buffer is written out to disk in single write operation. Okay, so when we say, so on top level we are using stream, but ultimately stream is only creation of the file system, the high level abstraction, right? The lower level is file descriptor. So ultimately there is corresponding to each stream, there is a file descriptor. Okay, so when reading is done, then data is brought to buffer, and then reading can be done from there. Okay, so it can be one by one byte, and when then buffer, something is to be read which is beyond the buffer size, then the next buffer can be brought in, right? That can be the design that library providers can think of. All right, so overall there is a less system calls. All right, so now let's look at the operations. Okay, so we know now that when we are using library, we don't use file descriptors. Then we are using streams that we call as a file pointer. Okay, so we call it file pointer, as I mentioned in third bullet point. Okay, and this file pointer is of type file. This is a new file type. There is a new type def, okay, which is of type file, which is nothing but is a stream. Okay, very similar to FD, which is file descriptor. Okay, all right. So streams may be opened for reading and writing or for both. So stream is similar to what we have seen earlier. So this function, so for example, if we have the function f open, so f open gives us, if you run this instruction, execute this instruction f open, and then give the file name, which is given as part of path, and then the mode, say read mode, then this operation will give you a a file pointer, which is a stream, which gives us stream. Okay, so this function opens the file, and the behavior is given by the mode and associates a new stream with it. It is nothing but an identifier. Okay, an integer number and so on. All right. So what are different modes we can open a file? Okay, these are the modes. We can open it for reading. So it means that now if you are opening something for reading, it must exist. All right. So you would have, I'm sorry. When you R is for reading. So when you're opening something for reading, then it must exist. It must have been opened. Okay. Because first operation you do on file, it is opening the file. And we have seen in the last class that what does it mean by opening a file. Okay. And when we open a file for reading, then stream or the pointer is positioned at the start of the file. Okay. Now second operation is writing. When we open for writing, if the file exists, now suppose you use this W, here in the last argument mode. Okay, and if there exists a file, then it will be, that file will be truncated to 0 length. Okay, and the file doesn't exist, then it's created, and the stream or the position is at the beginning of the file. Okay, third mode is append. It opens a file for appending. Okay, okay, so now if the file doesn't exist, then it's created, and then now here note the position of file. Basically a pointer, we will use a word, or a stream. It is at the end. Okay, so it's this thing is at the end, and the right hand side, because now appending operation can start. Then we have R plus, which is open a existing file for reading and writing. Note that R is only for reading while R plus is for writing. Okay, and if file and the stream is positioned at the start of the file. Okay, write plus is open it for reading and writing. It's truncated to 0 if it exists. Note that whenever we write into file, it's always truncated to 0. Okay, and if file doesn't exist, then create the file, and obviously the pointer or stream will be at the beginning of the file. Okay, and then we have mode as A plus, wherein we open file for reading and writing and create it if it does not exist. Okay, and read from the beginning and write as append. Okay, the stream is positioned at the end of the file. All right, so these are the operations. Any question? Opening a file is something like this, that first we'll have to define what is, a stream of type file. Okay, it's basically a new type def, and then we'll say stream is equal to f open is like file descriptor. Okay, uh, so it's a file pointer here, that's what we call it, is f open the path or the file name and the read mode. Okay, and on failure, if it's not able to open, then it gives null. And so instead of giving an integer number which corresponds to stream, it will give 0 or null. Then we can find out that there is something happened, so we can write a routine which is a small program. If it is error, then do something. All right. Okay, now let's look at what's the difference between uh, file descriptor when you're using syscalls, direct syscalls, and when you're using the functions given by library. So let's look at the one here. So first is directly using syscall. So it's a we'll get fd, which is file descriptor, is some integer number. And when we do open a file, say foo.txt, and we have to define a mode or rd only. Now, even if you interpret this could be, obviously we can make out that it's a read only, but there might be a more details about it, which when you go through syscall and all this argument, then we'll come to know. And these are too many actually. I mean, number of parameters, number of arguments that you can define are just too many. All right. So as a result of that, what we'll get? We'll get an integer. So fd, we get this integer 3. Okay, and then of course this fd will be stored in stack. Okay, runtime stack. All right, because all variables are kept there, so this is also kept as a part of stack. Okay, and when we use stream or library call, like which says that fs, which is of type file star, we use f open, then we define file name, and then let's the mode is w. Okay, so what we get here is as a result of this, of course this will be a number, okay, which will point to a buffer. Okay, we shall point to a buffer, and now this buffer obviously will be created in user space and can only be part of heap. Okay, it's or maybe by design it's made to be part of the heap. Okay, it cannot be part of stack because usually is a big size. Okay, and this file can be used by multiple processes, and the okay, so it's a part of stack. Obviously, when that the process that is making a call and this buffer is part of stack, it will go away. Okay, so it has got to be part of heap. Note that there is another file descriptor, right? Now this corresponds to the first instruction where you are using syscall. So 3 is there, fd is equal to, there is something called fd1 is equal to 4. This corresponds to the stream that we are using, because internally it will be converted into a syscall. Okay, so there is a file descriptor. When this buffer is kind of full, or when this library decides to, for example, write it back, then it will use this file descriptor 1 to push all the data in, right? So now it means that there must also be instruction in syscall where you can push certain length of the data directly into the disk. All right, any question? Okay. All right. So we have seen opening a stream. Okay, then there is similar to this is closing the stream. Okay, so you can close the stream, very simple. So if there is still some data left out while closing is is flushed out. Okay. All right. So what do you mean by flushing? Is it discarded or returned back to the disk?
Return to disk.
Okay. All right. All right. Good. So now, of course, we know this, right? That 3 standard files are always open. And correspondingly here, 3 standard streams are always open. Okay, and when program is executed, which is std in, std out, and std error. All right, so this we know. So let's not discuss this any further. Okay, and then there are multiple other functions that we can do when, for example, when we writing, then library provides multiple functions which are of simple nature. Okay, which ultimately gets translated to system calls which are more complicated, right? So first is f get c. We use this when we want to read character by character, right? So we say f get c and then define file, and then here we define stream that we have opened. Okay, which internally is actually some number, but we use a variable name. Okay, it's kind of is kind of a name. Okay, it and that you have to define the program. Okay, so instead of stream, you can call it when you're doing this operation. Okay, here we have used fs. Okay, so you can use any name, and then some integer is assigned to it, which corresponds to, which is unique, such that it can point out to appropriate place. Okay, now you have to think about it. Maybe I will ask in the exam, this uniqueness is with respect to process or system. Okay, just think about it. We'll get back to, just think, maybe I will ask this in end sem exam. Okay, all right, so this is f get c, you will get character by character, and so file, and you'll have to define a stream, and it will get assigned it return unsigned character cast to an integer. Okay, now note here, so you will get as a part of this, you'll have to of course write the complete this thing. Okay, instruction, how we are going to use, the way we are going to use this instruction. So the return value of this is not of character type but of integer type, which is typecasting, because of certain design advantages. Okay, all right, and when we read a character, it advances the current position in the stream. All right, similarly there is second function that we have seen, f get s, which reads the complete file. Okay, all right, and then we can, okay, what is the third one? Okay, the third one is corresponding to reading a binary data. Okay, so instead of reading characters and so on, we can, or line is nothing but a complete this kind of string, of course terminated by some character. We can just do read binary data, and then we have to define here what is size of the data we want to read. okay, in terms of number of bytes. Okay, and here also you have to define where you are going to store it. So for example, if you say void, so sorry, fread void buff size and size nr and stream. So stream tells you from where to, okay, and then it reads up to nr elements of data, each of certain number of size, into buffer pointed by buff. Okay, so now what we have looked at the parameters inside a function, inside this library provided function, and we have to define the parameters inside, which will obviously be certain. First thing here, okay, what is the size of the data that we want to read, and from where, which stream. Of course, stream we have to define, which is nothing but similar to file descriptor. Okay, and file descriptor or sorry, stream will have a position, current position. From the current position, you'll have to read data of certain size that's defined by second and third parameter, and it has to be kept somewhere. And where is it to be kept is defined by buff. Okay, now note that when we do this, data is already available in the buffer, not this buff, but the buffer maintained by library. Okay, this buff is nothing but user defined, you know, space where you can get this data from library buffer to user defined place. All right, any question? Now can you explore okay, what are the parameters being used in different functions? It will be very straightforward. Okay, and how we are going to use that? Okay, all right. So for example, here in this second case, when we are getting a line, is clear that we are going to get a string of certain size, okay, from the stream and put it into the user defined string where, say str. Okay, rest are all details, like, how do you find out where is lines terminating and so on. Okay, all right. So writing into the stream is very similar. So we use f put c in c and file stream. Okay, similarly we can write string of characters and we can write binary data. Okay, and then we have concept, right now when we are doing reading and writing, we can do it sequentially or we can define from where we want to do it. Okay, and that's called random access. So we have something like, and the operation is called seeking. So operation like f seek from some stream. Okay, we have defined that name of the stream, and then we have to define offset. And offset from where? Like basically we are trying to position that stream, or a pointer in that stream which is moving. Okay, so it's like this. Okay, the pointer is here. Okay, at this point in time. So if suppose from this point, we want to do the reading. Okay, certain number of bytes we want to read from this position onwards. So we'll have to define this position. Now we can define this position with respect to what? We can define this position with respect to beginning of this buffer or end of this buffer or the current position. Okay, all right. So all right, so now let's assume that we have to define a starting point few bytes away from the current position. Okay, so current position is shown here. You can see the blue arrow, and after a few bytes from that. So how can we define from current position? We can define in this way. Okay, the offset is from the current position. So we say seek curve. So Vance here is nothing but the current. We'll have defined seek current position. Okay. Now Vance is this parameter which is given is the beginning. Then we'll have to set parameter this Vance argument as seek set. Okay, which is nothing but from the beginning, or it can be from the end. When the value of Vance is seek end, we are actually positioning this pointer. New position of the pointer will be with respect to the end. So these are the three ways we can do that. Okay, so this sets file position pointer to a specific position. Okay, all right, and offset is tells you how much, and Vance tells you from where. Okay, from start or from current position or from the end. We'll have to use then offset value to go to the new position of the pointer, file pointer, or position pointer, sorry. Okay, all right. Any question? No?
No, sir.
All right, let's move ahead. So a large number of operations are given, which are available from library, and which is simple in nature, right? So you can just go through it. To summarize, okay, so basically what we have studied earlier is that we use syscalls for doing file operations. Okay, and we know the syscalls are quite expensive. Okay, while we user programs don't care about how files are organized in disk. Okay, and even for doing few byte manipulations, reading a few bytes or writing a few bytes will require a use of a syscall, and as a use of syscall, kernel will get the complete block from the disk, because the block is a minimum unit of transfer between the kernel and the disk. Okay, and so even so, in order to write many bytes one by one, you'll have to do so many syscall, and so many times block will be brought in from hard disk. Okay, so instead of doing that, the library takes care of this by bringing the whole block or multiple blocks into the buffer, and it does the manipulation and then finally writes it back into the disk using just one system call. Okay, all right, that's it. So now the question is that when do you programming, which one you will prefer? It depends. It depends on what your program is trying to do. It's just doing one syscall, one file reading, of certain number of bytes. Then you can as well use syscall. If you are doing a program is doing repeatedly, reading and writing into file, a lot of file transfers are there. Then you will as well like to use library. Now, what problem this library can cause? Can you think of this? No, I'm sure there must be certain disadvantage, right? Can it cause some inconsistency problem? This file is being used by multiple processes, right? And then one process is doing right for quite some time, doing read and write from buffer, while other processes directly change the contents in the file. Okay, so the order in which these operations are performed may be known to user and has done programming like that, but OS may do it in different order. May. Okay, what else could be disadvantage? I'm just thinking. I don't know. I have not read it from the book, but I'm just thinking. What could be other disadvantage? Think about it. All right. Okay. Thank you.